Okay, I'll give a brief introduction to the Grin proof of work so that Wilke can take it from me and present some nice breakthroughs that he's recently discovered. So let's start with the basics. What is a proof of work? Basically, it's a puzzle that has to satisfy several properties in order to be useful for cryptocurrencies. Of course, it has to be very hard to solve. It would also preferably be very easy to verify so that people don't waste time trying to identify the branch with the most proof of work. And then it has to be tied to some message, which means that you won't be able to reuse any old proof of work. You have to keep on finding new ones, and they have to commit to some data. Here's an example of a puzzle that's very hard to solve. Don't have time to go into details about that one, but there was a £1 million prize on that was claimed after less than a year. So the topics I will cover in this brief introduction is beyond what is proof of work, the origin of the Cuckoo cycle proof of work, which is hash tables, and in particular the Cuckoo hash table that leads to the notion of a Cuckoo cycle, which this proof of work is centered on. And then most of the work in solving this proof of work, in finding the solutions, turns out to be a process called edge trimming. And from after that, Wilke will take over. So a proof of work is a key ingredient in cryptocurrencies. They're used for two purposes, both to establish consensus, so that everybody agree on what is the longest chain of blocks that everybody should be considering the true state of the blockchain, so that everybody can try to extend that longest chain and agree on which transactions have taken place. But equally importantly, proof of work serves as a mechanism to fairly distribute all the new coins to people. And for that purpose in particular, you also require this fourth property, that you can randomly generate puzzles with a known difficulty. And that lets you adjust the difficulty dynamically and make sure that on average your blocks come in case of Grin, every 60 seconds. So most people, when they think of proof of work, they equate it with the notion of the particular instance of proof of work that's known as Hashcash. And that's because that's what Bitcoin uses, that's what most every other coin uses. So in that type of proof of work, the puzzle you're trying to solve is to find an input, n, to a hash function, to one input together with some message, for instance, like the previous block that was found, such that the output of the hash function is very, very small. So you can lower this threshold to make it harder to find a solution to this. This is very nice and simple. We don't have a good way to predict the output of a cryptographic hash function, except just to try many, many inputs. So ASICs all over the world are trying trillions and trillions upon random inputs to the SHA-256 hash function. All these chips are computing them in parallel, and at some point somebody finds a very small output, and then they can announce their newly solved Bitcoin block. So in this case, the verification is exactly the same as doing a single attempt. You just compute the hash function. So it's an example of a symmetric proof of work. There are a few more interesting instances of asymmetric proofs of work, where trying to find a solution is very different from verifying the solution. First instance was in 2013 in something called prime coin, where you're trying to find particular patterns of prime numbers known as Cunningham chains. So these are a series of almost doubling prime numbers. So 11 is 2 times 5 plus 1, and then this is 2 times 11 plus 1, and this is 2 times 23 plus 1. And these are all primes. And you try to find even longer ones. And you pick the prime number with a very special pattern so that it actually commits to some data. Later that year, there was a proposal for a proof of work where you simply want to find a birthday collision. So two inputs, different inputs, that have the same hash outputs. Unfortunately, this turned out to have some weaknesses, but this is partly what inspired me to come up with Cuckoo cycle, which can be viewed as a generalization of this, where you don't have a single collision, but a sort of like a 42-way collision. And a year later, there was Equihash, another asymmetric POW, where you basically try to find a two-power number of different hash inputs, such that the exclusive OR of all the outputs is 0, and there are some additional conditions. And this has found successful use in Zcash and many copies. So it has taken a bit of time for Cuckoo cycle to be adopted. It was published first in January 2015, but only now is used in Grin, and actually was used a little earlier in another coin called Eternity. So Cuckoo cycle is inspired by hash tables. Hash tables are a simple linear data structure in which you can store elements and retrieve them fast. The idea is if you want to store some data item, you compute a hash function over it that gives you some arbitrary index in the table, and then you look to find the element there, or if it's not there, you try to put it in one of the successive slots. So when you're storing elements, you go to the location directed by the hash function, and if you find an empty slot, you can store it there. If it's occupied, you go to the next available slot. What does it mean for looking up data? It means you go there and look at successive elements until you find the one that you're looking for, or until you find an empty slot and then you know it's not there. This is very popular. It's used in many programming languages as a basic data structure, also known as associative arrays. In this variation called a Cuckoo hash table, you have the nice idea that you have two separate tables and two separate hash functions, and an element can occur at only two possible locations, namely either the location indicated by this hash function in this array, or by this hash function in that array. Only two possible elements, places you have to check to see if the element is there. That's nice. But how do you store elements? In this case, if one is occupied but the other is available, okay, I can store 8 there. But what if the other one is also occupied? That means you're going to have to do what this bird would do, kick out one of the elements and put yours in its place. So in this case, we kick out 11 from here so that we can store 8. And now what do we do with this 11? Well, 11 had one other possible location in this array. So we hash 11 to see where it should go. But perhaps that is also occupied. And that means we have to keep going a bit. In the end, you can represent the state of this with a graph like this, where for each element you point with an arrow to its alternative location where it could have been. So 19 is stored here, but it could also go here. 11 is stored here, but it could also go there. And this works fine as long as you have a nice acyclic structure. But once you reach a cycle in this graph, like here, you see this points here, points here, points here, and then comes back here. This means you won't be able to store more elements. If I have an additional element 7, for instance, that can either go here or here, then because I have 6 elements now that I want to store, and there's altogether only 5 locations they could go to, the pigeonhole principle tells me I cannot fit 6 objects into 5 places. So that would mean you have to re-index your whole data structure. You have to make more space. But this is actually the failure of this data structure to store all the desired elements is actually what we're going to be looking for in our proof of work. That's the solution, to find a cycle in such a graph. So we randomly pick n edges between n nodes here and n nodes here. And the way we do that is we just have edge number 8. We compute the endpoints with the 2 hash functions. And among these n edges, we're going to look for a cycle of a certain length. Here's an example of such a Cuckoo graph, this one having 2 to the 8 edges. And if you increase the number of edges to 4096, it looks something like this. And as you can see, it's kind of hard to figure out if there's a cycle in here. But this is a nice task for a computer to solve. It's going to take you some luck, because it may not have the cycle of the length you want, and it's also going to take you some memory and some computing cycles. We can mathematically compute the expected number of cycles of a certain length. I won't go into the details, but basically the idea is that a cycle is represented by this sequence of edge indices, and you can choose them in about, for a cycle of length 42, you can pick a sequence of indices in n to the 42 ways, but also the probability of each of these pairs of edges meeting in the same point, because there are n nodes here, has only a chance of 1 over n. So you raise that to the power of 42 for all the coincidences forming a cycle, and then it sort of cancels out, and you find there is an expected number of 1. But these are not cycles, these are anchored cycles, because I chose to let the sequence start at a particular edge. I could have picked any of the 42 edges to start this sequence. So if I consider the number of unanchored cycles, it turns out to be 1 over 42. So a random Cuckoo graph has an expected number of 1 over L edges of length L. And here's a precise formula that takes account of the fact that I don't have infinitely many n, but I do have to make sure that my edges go through different points. So there's 2 separate algorithms that we use to find 2 possible algorithms we can use to find cycles, but actually our miners spend most of the time not finding cycles, but doing something else. So I'll skip through these because we don't have that much time. The Cuckoo cycle miners spend most of the time doing edge trimming. Look at this graph. We can see that there's an edge here going to a leaf that no other edges are adjacent to. That means that any cycle will not be using this edge because there's nowhere to go. So such an edge can be trimmed. And similarly, there are other such edges going nowhere. So we can trim all of them. And in the next step, because of the trimming, we have new edges that end up on leaf nodes. That one and this one and this one. We can trim those. Then in the bottom, we trim, we keep on trimming until we're at... if you keep on trimming, we end up with this. Now there's nothing more to trim. This forms a cycle, so there's nothing more to trim. In practice, you don't have to keep trimming until there's only cycles left. You can just cut down until you have only like 0.1% of your original edges, and then it becomes much more efficient to do this actual cycle finding. Here is the edge trimming in action. We start out with 1,024 random edges. The first trimming phase already takes away a fraction that you can prove corresponds to 1 over e of the edges. So you're left with less than 2/3. And the second round of trimming is even more dramatic. You cut away more than half of the remaining edges, and then you keep going, and it thins out quickly. And if you were to keep going all the way, you would actually be left, in this case, with a 6th cycle. I'm hoping Wilke is ready to take it over from here to discuss how actually you could do this, implement this edge trimming.